So thank you so much for the kind introduction. Maybe next time or in some years I will be able to speak in Spanish, but still I try to explain things in English right now. But as you, Carlos, explained, the slides will be in Spanish. So the title is in English, Discovering Surprising Facts on Simple Geometric Figures with GeoGebra Discovery. And this is a kind of joint work. I don't know if you can see my screen. Can you see my screen?
Yes, yes,
okay.
No problem.
Okay, so this is a joint work with Tomás Arefio from University Santander in Spain, but he now works in Madrid together with Pilar Vélez. She's Pilar, and I usually meet them regularly, once a year or twice a year, so we work a lot together. I will copy the link to my slides in the chat. Maybe you can follow me also like that. Well, here I just copy. This is the file to the Spanish slides. And also, if you want to try the new system, then this experimental version of GeoGebra, it is called GeoGebra Discovery. You can find the newest version here. So Professor Almeida was an expert in the newest version of GeoGebra. I will use not this web-based version, even though it would be possible, but this old version written in Java for the desktop machines, this will be a bit faster. So I will use it. And in some cases, Carlos, you are actually an expert of real geometry. I chose a topic that is close to real geometry. Maybe later I will clarify this a little bit, not going into the very detail, but for real geometry, this version is a bit better because some more features are available. So here you can see that this is a special version of GeoGebra.
Yes.
This is the latest version, so 26th of May, and it is based on the classic version of GeoGebra, which was released on the 4th of May. Okay,
I'll try to check it out, Zoltán.
Okay, okay. So this is the web page where you can download it, and I will use a couple of regular polygons. So polígonos regular, and you will see, I hope so, at least. So these regular polygons will be used to show two tools in GeoGebra Discovery. The first one is quite well known in some sense, relation of two objects, and descubrir is something new. It is a kind of exploration, a kind of discovery of not trivial, sometimes trivial facts of geometric properties in a figure. So discovery, you know, maybe the story about an unsuccessful or not very lucky discovery. It was successful in some sense, but for this guy, Hippaso de Metaponto, he was a Greek mathematician in the school of Pythagoras. It was something negative because he learned something unusual in the geometry. And it was actually about the diagonal of a square. So let's try to repeat his exploration. So we create a polígono regular with 4 vertices, and we try to highlight this segment here, so between A and B. And now the well-known tool Relation will be used to connect A and C. No, first I wanted to create a segment. So first segment, this is denoted by J. And now I can try to compare these two, either clicking on these two segments or here in the Vista Algebraica. I can see that, okay, they are different, their length are different, but if I click on more, then I can learn that, well, there's a kind of relationship between them, square root of 2. And of course, in school, if you are not familiar with square root, it's safer to say nothing about this, but to change at options the number of decimals, the rounding accuracy, and okay, so this is a kind of strange ratio between the length of F and J. If I set it to, well, let's try to set it to 1 or almost 1, and it's maybe even better if I switch the grid on, and then I can put the points on grid points, so I have a unit length for this square, and I can see, okay, this is something strange, 1.4142. Well, this is quite well known at school. In Austria, in Hungary, and in many countries, we can prove, and we usually prove in high school, that this proportion is not a rational number, by using kind of indirect proof, a contradictory proof. Okay, we can continue this with different regular polygons. So let's try what happens if I just remove this one and create a regular pentagon. So a regular pentagon is a bit different, and I can try to connect again A and C. Actually, it doesn't matter, because the other ones, the other diagonals, are also of the same length. And well, if you are familiar with some properties of the regular pentagon, you can see, aha, so this looks like a number like the Gordon ratio. And it is indeed the Gordon ratio if you want to express it by using the square root of 5 plus 1 over 2, then you can have an exact number. And well, in fact, here we receive this information quite quickly. Well, I didn't tell you a very important detail here, that in the background, and now maybe Carlos has some overview on the background. Here we use not just a kind of algebraic technology by using an equation system, because you can have an equation, okay, how is it done? How it is learned by GeoGebra, by GeoGebra, that this kind of symbolic relation exists. Well, the complete figure will be translated into an algebraic equation system, but now we also need to have a so-called inequality, and these equalities as inequalities are written down here. This is not for the students, not for high school students. It's not for your family, and it's not for you. Actually, it's a very hidden information in GeoGebra, only for developers and researchers and those who are working hard on this. But you can see that these coordinates V19, V12, V13. So this is actually a faithful translation of the geometric figure into an algebraic equation system. And sometimes, if we want to be as accurate as possible, then we need some inequalities. And now, by using this tool, it is called Tarski. Tarski was a Polish mathematician. He invented a lot of notions, a lot of techniques in this topic. So the name of the program in the background, this is a free program, and we use it to extend the possibilities of GeoGebra to compute these results. Without this, we cannot uniquely determine this number, and the web version of GeoGebra doesn't have this feature. So you will have two options, either one number or another number. We will see later how this works if Tarski is not present or Tarski cannot tell for some reason such a detail. Okay, so this is a regular pentagon, and I will do the same for a regular hexagon. I think it's quite simple in the school, in your class. If you want to learn this length, it's not a very difficult question, but so for the first look, I would say this is a square root of 3, and it's not very difficult to prove it. Also, if you connect this one and this one, so you have 2, and well, we can get the same very similar answer by using GeoGebra Discovery here. So I created a table to summarize what we can learn by using GeoGebra here, and it's clear that not just the magic number square root of 2 is problematic for the Greek mathematicians, and so we could be sentenced to death, not just because the diagonal of the square, but also for the diagonal of a pentagon or a hexagon, unless we use the diameter. And this fact will be actually continued for bigger numbers, for bigger sites. I will show you how this works, because it's actually quite quick in GeoGebra. So I remove again this, and let's see what happens if the number of the sites is 8, and I can connect again these two. I can find the relation of these two ones, and now the computation is a bit longer, because here Tarski is taking over the important steps, and well, we can see that we used 2 square roots to express this number, this proportion, and you can find very similar results for this length or for this diagonal. I'd like to show you that these 2 ones, so maybe you can discuss this question also at school. So this one and this one here, the ratio of them is very similar to the previous value, because, and you will see very quickly why. Well, this is a square root of 2 times square root of 2 plus 2. So this number is quite close to this one. The only difference is that here there is a factor 2. Can you see it? So here there is a missing 2 here. Well, I think it's quite easy to tell why this difference is here, because if you create let's create a simple polygon. So this one maybe, and I will change the color of this to green, for example. Then I think you can see that this is a right triangle. Here is the right angle, and this diagonal is the same long as this one here. So it's quite clear that we have a triangle with sides 1 to square root of 2. So this result is here actually quite reasonable. What can we say if we go one step further? So if we have a regular decagon, you may ask why I missed number 7 and number 9. Well, we will answer this question very soon, but I wanted to go in a direction which can be in some sense discussed in school as well. So I don't think it's very simple to handle the case with the regular heptagon, so the polygon with 7 sides, and the case with 9 sides. And we will learn the reason very soon why this is the case. But first, I want to create a regular decagon to show you how beautiful the result is if we want to read off the length of the diagonals. So let's try again. I will compare this length and this length. So there seem to be again some difficult. This seems to be some difficult ratio, and in the background, unfortunately, Tarski doesn't have a positive answer, so you can check. Aha, it's going to time out. I don't know if you can see this quite nicely. So I zoom in a bit, and then you will see maybe that here is a timeout. A timeout means in computer science, in informatics, that something was too difficult, and that's why there was no computational result. So GeoGebra tries to do its best without using the Tarski system, and it cannot exclude some possible cases. That's why 2 possible answers exist. I will not show, but you will try that the other diagonals will give some quite similar results, and the number square root of 2 will appear many times. So there is a very similar, so these are very similar, these cases are similar to the case of the regular pentagon. Okay, what we can conclude here? Yes, I wanted to show you something more on the regular heptagon, and why not? Maybe we can go back to this regular heptagon. It's a bit different. So we don't have a beautiful. It's a question if it is beautiful or not. So it's different. If we compare these 2 diagonals, and this diagonal and this side, then we have actually a unique answer from Tarski, but the unique answer is, well, a number that is not clear what this is. So let's go back to Tarski, and we learn that actually this number is a root of a polynomial that is so-called cubic polynomials of degree 3, and that's why we cannot express this number by using only the first basic operations and the square root. Okay. Another slide shows a quite new result from Giovanni Vincenzi, and this is about to explain if we can have actually a rational number or not in our case. And Vincenzi proved last year that it's not possible only for a regular hexagon, or if you have a regular dodecagon, or so on. So with sides 18 sides or 24 sides. So it's a quite nice result. You can see here in the internet if you want to have an explanation why this is so. On the other hand, we can learn a bit about the famous theorem of Gauss-Wanzel. It's quite an old theorem, almost 200 years old, and we need the definition of the Fermat numbers or Fermat primes for that. And these Fermat primes are the basis for to build actually regular polygons that are constructible or not. So what is a constructible polygon? Constructible con regla y compás. So with a compass and a straight edge. Okay, regla y compass. So a regular polygon can be constructed if there is a number, if the number of the sides is in of this form 2 to the k times p1, p2, and so on, pt, where these numbers are prime numbers, and all of them can be only 3, 5, 17, or the last two ones. Maybe we can play a little bit to see if you are good at deciding if a regular polygon can be constructed by using compass y regla. So regular triangle, is it constructible? Yes, yes, see, it is. And also a regular fourgon, a square, it is again constructible. You can do it at school. A regular pentagon is also possible, but not so trivial. You need to create somehow a diagonal square root of 5 and then play a bit with these properties. A regular hexagon is also possible, but a regular heptagon is not. So it's not possible. And even if the regular octagon is possible and it can be constructed, the regular nonagon is not, and the regular decagon is possible, and so on. So we can use this theorem to learn if something is can be constructed or not. So let's go back to connect these two things. So if you use this theorem that something is not constructible, we can find, so this is a kind of connection between the constructibility property and if we are able to express the diagonal by using the first operations, the operaciones básicas, and the square root, raíz cuadrada. So this is the clear connection. You can think about it, why this is like that. I wanted to show you another tool, if I have 2 or 3 more minutes, because this is also something new and something more visual that you can offer for your students to make mathematics more interesting and surprising. If this was not surprising enough, then maybe this next topic will be a bit of surprising, and that's why I chose 3 figures. The first figure consists of a regular hexagon and a regular triangle. The next one, square and a regular octagon, and the last one, a regular pentagon and a regular decagon together. Maybe we can select the last one. It's quite simple to construct this both together. So let's try first a regular pentagon, and let's create then the regular decagon. And now we have this strange figure, and I will use the tool, the Discover tool, to find some interesting properties of one of the points. So which point should I choose to learn something interesting? Well, it's my choice. I will use D because it seems it's somewhere in the middle, but maybe, well, I'm just starting my computation, and here I can see that GeoGebra is working hard. In version 5, in the desktop version, it's much faster. In the web version, which was used by Professor Almeida, it works, but it's not so quick. So that's why I'm using here this faster version. And after the information is collected, so every piece of property, like equal long segments or perpendicular ones or parallel ones, so this is collected. also if some points are collinear. So here, this is a report on puntos colineales, puntos concíclicos, líneas paralelas y perpendiculares, and so on. So this kind of information, pieces of information are shown. And also, if I want to see, so I can check things here in the figure, and maybe this one is quite strange. Why is it true that the points C, D, and H and G, so they are concíclicos? Well, you can play with this new feature if you download, or if you just start GeoGebra Discovery. I think I will send you a link, which is also an online version, and you don't have to download anything if you don't want. So this is a demo version, a bit limited, but it works also for this. Okay, I think that's all for now, and thank you for your kind attention. Well, where I can see my slides here. Okay, so I created two figures for you with a square and a regular octagon, this final figure. And maybe you are interested in the bibliography. You can see that I work a lot with Tomás and Pilar. So this is a kind of collaboration among Spanish and non-Spanish people. So thank you so much for your kind interest. Muchas gracias.